same thing. Questions will be from the lecture. Questions will also be from where? Homework. Okay. If you look at the amount of questions we have done, it's about 20 to 22 questions. But as you all know, I can combine 2 questions into one in your term test. Are we clear? Okay. So if you were to do your homework on your own without the solution manual and also understand the examples that I teach, you should be fine. Are we clear? Okay. I'm not here to. This course is not that bad. Okay. It's a 3A that you are going to die. Okay. So, right. So let's continue with our example that we have done. Okay. And I will, maybe some of you forget where are we. Okay, I will highlight what's the problem and some key things to take out on. And I think I'd like to elaborate one more point that I made yesterday that I don't think I did a really good job on it. Right, so what we are going to find over here is we are going to, so if a question like this come out in your term test, I will highlight that determine the angular velocity of rod ACD at the instant shown using IC method. Okay, so using instantaneous centered method, I'll highlight that in those questions. So, okay, right. So with the IC method, okay, note when using IC method, okay, direction of velocity vector must not be what? Must not be assumed. You have to be very, very sure about the velocity vector. Okay. So for this question, we want to determine what is our omega CD. Okay. So how this thing is propelled is we are given omega AB is equal to 3 radians per second. Okay, so we are given a boundary condition. Or we are given a few boundary conditions. That omega AB is equal to 3 K radians per second, positive. And then we are also given other boundary conditions which I forgot to highlight. Okay, so the other boundary condition is at point D, right? Point D, we know it is what? It is spin. Okay, in fact, point D, point A, and point D are pinned. Okay, so given that this is spin, we know that velocity at point A is equal to velocity at point D, and they are what? 0 meters per second. Okay. So from here, again, we identify our rigid body. Okay. So rigid body are what? Member AB, that's a rigid body. Member BC, that's a non-rigid body. Member CD, that is our rigid body. Okay, so the only thing that we are sure for now, okay, based on this diagram, okay, anything that you need to clarify, you stop me. Okay, I'm looking at my screen, just say excuse me. Are we clear? Okay, don't just sit out there and just do nothing. So we know we have a velocity vector over here. This is our VB. And we are very sure that VB relative to the member AB, this has to be what? 90 degrees. Why it has to be 90 degrees? Because it's rotating about a pin end at point where? At point A. Okay. So we also know that over here we have two velocity vectors. I mean, two components. One is in our I direction, okay, and the other one is in our J direction. And we know that this is how many degrees? 45 degrees. Okay. So from here, we know that this is 0.707 VBI. This is minus 0.707 VBI. And the other one, sorry, I beg your pardon, is VBJ. Because it is 45 degrees. Sorry, okay. If you leave this there, okay? Because we don't know yet. So our concern is we have to find the angular, so we have to find, okay, what we have to determine is we have to find omega CD, okay? We have to find omega CD, okay? So from here, right, we are going to focus on the rigid body BC. Okay. And we know that LBC cannot change in length. That's why we call it rigid body. Wait, right? So one thing for sure, right? If we were to, because yeah, I like when students ask me question, and if the logic is not right, I don't like it. My logic is not right when teaching is not good. If I were to divide this into 4 quadrants, okay, we are very, very sure that VCI is going to be in this direction, or I'm going to call this alpha VCI, right? Then there's two possibility. The two possibility is it possible for beta VCJ to be going up, or is it possible for beta minus VCJ, right? So if we were to assume one, if we assume this direction, right? I mean, this is not a very good direction to assume, but okay. Oh yeah, okay. Let's say we assume this direction, okay, for argument's sake. That is our VC. And then the other one, we assume it coming down this way. So VC number 1, VC number 2. Is it possible for VC number 1 to happen? knowing that it's on the second quadrant from point D. Is it possible? Yes, why, no, why, you can call a friend. Come on, anyone. Yes. So you just identify the first thing to look at, okay? Because it's linked to the what? It's pinned down at point B. We also know that VC vector relative to CD has to be how many degrees? 90 degrees. Okay. So that's one reason why it has to be VC2. Then why is not VC1? For the same reason, what is the other reason? If beta BCJ is going up, the length CD has to what? Change. Based on the second quadrant, this is the first. Are we clear? Does it make sense now? Okay, so there are two things for you to check, right? So the best identifier is your I direction, like what I said. Okay. And then the next one, you can look at the J direction. And one of the things to confirm is BC has to be 90 degrees to the linkage. Okay, CD. Okay, I'm going to copy this again. You don't do anything because this is a big mess now. Okay. No diagram. Oh, hold on. This has to work. I don't invest in Microsoft. They're screwing me up. Okay. Right. So we know, okay, I'm going to get rid of this, the earlier analysis. You don't get rid, okay, you leave it there. So we know that VCI or VC is coming down in this direction. So again, we are going to have a VC. We are going to have a VC. And we're going to rotate this left. Right. So we are aware that this is our VC. Okay. So from here, we know that this is 90 degrees. And then from here, we can construct we can apply our instantaneous center. So apply instantaneous center. This thing will go up to here. And then on our instantaneous center again. Okay. So this is 90 degrees. This is 90 degrees. Okay. So now we have our instantaneous center. Okay. So we have our points. Right. So what we are trying to find down here, okay, is we are going to determine VC. Okay. So after we determine VC, we know that VC is equal to omega CD RCD. Right? Then from here, omega CD is equal to VC over RCD. Okay, so that is the long run. That is what we are trying to, so that is the next few steps. But first of all, we have to determine what is our VC. So from here, okay, we are going to apply the instantaneous center